As you know, we have been working on the solution of the electronic Schrodinger equation for a hydrogen atom. In the previous modules, we have solved the angular part of the equation and got the corresponding wave functions, which are called spherical harmonics. In this module, we will be solving the radial part of the electronic Schrodinger equation. And once we get the radial part and we have already got the angular part, then we will be able to get the total electronic wave function of the hydrogen atom. As you already know that the electronic Schrodinger equation for hydrogen atom, if it is written in polar coordinates, it is shown here in equation 1 upon rr del by del r square del rr by del r plus 8 pi square mu r square upon h square. Then in parenthesis we have E electronic minus V parenthesis closed plus 1 upon theta theta 1 upon sine theta del by del theta sine theta del theta theta by del theta plus 1 upon phi phi plus multiplied by 1 upon sine square theta del 2 phi phi by del phi square equals 0. This is the total electronic Schrodinger equation, which we have already discussed, and you will agree, and as we mentioned it earlier, the first two terms in this equation, they refer to the radial part, while the last two terms refer to the angular part. And we also know that the total electronic wave function of the hydrogen atom, which one can obtain from the solution of this electronic Schrodinger equation, will be given by psi r theta phi, which will be equal to rr, which is the radial part, then multiplied by theta theta phi phi. Theta theta phi phi, which we also call as y theta phi, is the angular part, and we also call it spherical harmonics. Theta theta and phi phi, these have already been obtained in the earlier modules, and their expressions are written in these equations, and if we multiply them, we get the total spherical harmonics, which is y theta phi equals square root of 2l plus 1, then l minus absolute m factorial divided by 4 pi l plus absolute m factorial. Then we have plm x e to the power iota m phi. Here L is equal to 0, 1, 2, 3 and so on, and m varies between minus L to plus L. So this equation refers to the spherical harmonics, and these have been obtained in the earlier module. Now we will focus on the solution of the radial part of the electronic Schrodinger equation. The radial part of the electronic Schrodinger equation, as we mentioned, were the first two terms. Let's denote these two terms equals beta. That means 1 upon rr del by del r square del rr by del r plus 8 pi square mu r square by h square. Then we have E electronics minus V equals beta. This is the radial equation. Please note that in this equation, we are not replacing mu r square by moment of inertia. Why? Why can't we replace it? It's not replaceable because r is a variable and it's not a fixed quantity. Now, if we have to solve equation, what do? We solve this equation by a factorization technique. But before we apply factorization technique, we have to reduce this equation to an equation which can be factorized. And now we will focus on how to reduce equation to an equation which can be easily factorized. First of all, In this equation, let's assume 8 pi square mu upon h square, then E electronics minus V equals A. Let's assume this whole to be equal to A. And if we make this substitution, and secondly, we put beta is equal to L into L plus 1. If we make these two substitutions in equation, then our equation becomes, as you can see here, 1 upon RR del by del R square del RR by del R plus AR square minus L into L plus 1 is equal to 0. Please notice here that V is the potential energy, which is attractive and therefore with the negative sign, and is equal to minus ZE square upon 4 pi epsilon 0 R. And if you remember, in the previous module, we said that theta equation was reduced to Legendre's equation, and there we defined beta is equal to L into L plus 1. So all the things are now very clear, and therefore now we have equation, and this equation now we will further modify. As I mentioned it earlier, equation is difficult to solve directly. Therefore, it is reduced to an equation which can be easily factorized. So how to reduce it to that equation? Let's look at the steps carefully. First thing which we do is that we multiply equation with RR by R square. If we multiply, we get, you can see 1 upon R del by del R square del RR by del R plus A multiplied by RR multiplied by R minus L into L plus 1 R by R square equals 0. So this is what we get. Now look at the first term of this equation. The first term of this equation is 1 upon R del by del R square del RR by del R. This can be written as del 2 by del R square RR multiplied by R. Now these two are equal quantities. So this can be shown. You can see, if we have to prove that these two quantities are equivalent, you can see we are taking the left hand side here. Left hand side is 1 upon R del by del R square del R by del R. Therefore, if we open it, it becomes 1 upon R, then R square del 2 RR by del R square plus 2R del RR. It is a simple differential which we are doing by parts. And this on further simplification gives you R into del RR by del R square plus 2 times del RR by del R. Now if we look at the right hand side also you can see, as it has been shown clearly here, that it's a double differential. So we take first differential, and first differential is del by del R, then it becomes RR plus R del RR by del R, and this becomes equal to del RR by del R plus R del 2 RR by del R square plus del RR by del R, and that becomes equal to R del 2 RR by del R square plus 2 del RR by del R. That means left hand side is equal to right hand side, and therefore, as we said, the first term of equation can be written from this equation. You can see this equation is now del 2 by del R square plus A minus L into L plus 1 upon R square, parenthesis closed, RR dot R equals 0. Now this is the equation which we have got. Now we substitute back the values of A which we made the earlier substitution, and after substituting the value of A, our equation becomes, as you can see here, and if we do some modification, our equation becomes del 2 by del R square plus 8 pi square mu upon h square E electronics plus 8 pi square mu upon h square, then in parenthesis we have Z square upon 4 pi epsilon 0 parenthesis closed 1 by r parenthesis closed minus L into L plus 1 upon r square parenthesis closed r dot r equals 0. Now in this equation we substitute 8 pi square mu upon h square into E electronics equals W. We are making this substitution, and we are also making the substitution that 8 pi square mu upon h square in then Z square upon 4 pi epsilon 0 equals k. Now once we make these two substitutions, we get the equation del 2 by del r square plus W plus k by r minus L into L plus 1 upon r square parenthesis closed r dot r equals 0. Now we make one more substitution, and that substitution is that let r dot r be equal to FL. We are making a substitution because r will vary with the quantum number L, and therefore once we make this substitution, then in that case our radial part r can be expressed as equal to FL by r. And once this substitution is made, we get equation as shown. This is del 2 by del r square plus W plus k by r minus L into L plus 1 upon r square parenthesis closed FL equals 0. Now this is the equation which can be easily factorized. So you see here that we started with the radial equation and did some modifications, and ultimately we got equation which can be factorized, and through that factorization we can obtain the radial function and then ultimately the electronic energy. So in this module today we have studied the radial part of the electronic Schrodinger equation. If we recall, how did we start? In our earlier modules, we started with the fact that hydrogen atom is a two-particle system. We wrote its total Schrodinger equation. Then we separated the nuclear part from the electronic part and ultimately got the electronic Schrodinger equation. And this electronic Schrodinger equation was reduced to polar coordinates. And once we had this electronic Schrodinger equation, from this one can get the total electronic wave function, which will be the function of the three coordinates r, theta and phi. And that will be equal to r, which is the radial part, and then theta, theta and phi, phi, which is the angular part. This angular part is also known as the spherical harmonics. Now the total electronic Schrodinger equation which we have got, now in this equation, which is 1 upon r del by del r square del r by del r plus 8 pi square mu r square upon h square, then in parenthesis E electronics minus V parenthesis closed plus 1 upon theta theta, 1 upon sin theta del by del theta, sin theta del theta theta by del theta plus 1 upon 5 phi phi, then 1 upon sin square theta del 2 phi phi by del phi square is equal to 0. The last two terms of this equation were the angular part, which we solved in the last module, and we got the spherical harmonics. In this module, we started with the first two terms, which is the radial equation, and we started with the radial equation, substituted the value of the beta. As you know, beta was equal to L into L plus 1. This came from the Legendre's equation, and after doing all this, we have been able to reduce the radial equation into the form, and this is del 2 by del r square plus W plus K by R minus L into L plus 1 upon R square, parenthesis closed, FL is equal to 0. Here you know that RR, which is the radial part, is equal to FL by R. And we also know that W is equal to 8 pi square mu upon H square E electronics, whereas K is equal to 8 pi square mu upon H square ZE square upon 4 pi epsilon 0. Now this is the equation on which we have to work further. And in the next module, we will see how this radial equation, this modified radial equation, can be solved using the factorization technique to obtain the radial part of the electronic Schrodinger equation.